Section 5.2, we're going to talk about the definite integral. In section 5.1, we spent time learning about sums with the sigma notation, in particular Riemann sums. What we're going to do in this section is take some of those sums and redefine it or reformulate it. So let's begin with the definition. If we have a function that's defined on an interval ab, then we say that the definite integral of f from a to b is given by this notation. Okay, so we saw this same notation in section 4.10, except without the little a and b part. So let's make specific what exactly we're talking about here. Okay, so I can see the integral symbol. Okay, and the differential tells me what the variable is. So the differential is part of the integral symbol. Okay, now we have this new thing. The a and the b are what we call limits of integration. And then, of course, we have the function that we're integrating that's sometimes called the integrand. And just to give us a little bit of context, if I have my function y equals f of x, and we have an a and a b, then the way that we've defined the definite integral as the limit of the sum of f of xi delta x is exactly the area under the curve that we talked about in 5.1. Okay, now part of this definition says that if the limit exists, then f is integrable, and we don't always know whether or not that limit exists, and that can be hard to figure out. So what we're going to do is have a theorem to kind of tell us when things work out nicely. And here it is. If f is continuous, then f is integrable. Okay, and that's going to be enough. As long as we work with continuous functions, then we know that everything is okay. Now, as a side note, other functions may be integrable, functions that are not continuous, but we're not going to look at those. Those examples would be very complicated, and we don't really need to deal with it to get done what we need to do in this class. All right, so let's go ahead and look at what it would take to evaluate this integral using this limit definition. We saw this a little bit in section 5.1, so let's just go through it again. So let's find the integral from 1 to 3 of 2x squared minus 3x plus 1 dx. So what I'm going to do first is I'm going to rewrite this. Since I want to use the definition, I'm going to rewrite this as the limit of a sum. So we have the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x, where delta x is b minus a over n, which for this example would be 3 minus 1 over n, or 2 over n, and xi is a plus I delta x, which is 1 plus I delta x. Delta x is 2 over n, so this is 1 plus 2I over n. Okay, in order to plug in here, I want to know what f of xi is. So f of xi is 2 times xi squared, so 2 times 1 plus 2I over n squared, minus 3 times 1 plus 2I over n plus 1. So let's go ahead and work this out. Let's simplify out as much as we possibly can, just like we did with the limit definition of a derivative when we would simplify out before we would plug back into the limit definition. So I'm going to go ahead and FOIL out 1 plus 2I over n squared. At 1 plus 2 times 2I over n plus 4I squared over n squared. Here I'll distribute the negative 3. Okay, and now I'll distribute the 2. So I have 2 plus 8I over n plus 8I squared over n squared minus 3 minus 6I over n plus 1. And now I'm going to gather like terms. I have 2 minus 3 plus 1. Those add to 0. I have 8I over n minus 6I over n is 2I over n. And then 8I squared over n squared. Let's bring that back here to my limit definition. So this f of xi, I'm going to place with this piece. So we have the limit as n goes to infinity of the sum from I equals 1 to n of 2I over n plus 8I squared over n squared, and times my delta x, which is 2 over n. So I'm going to do a little bit of simplifying. Take that 2 over n and distribute it. So I have 4I over n squared plus 16I squared over n cubed. And now I'm going to use the properties of sigma notation, and I'm going to break this up into two sums, and I'm also going to factor out the constants. So n doesn't change as we go through the sum because I is my counting variable. So this first one, the 4 over n squared, factors out, and the second one, 16 over n cubed, factors out. And here we're left with the sum from I equals 1 to n of I squared. Okay. Now what I'm going to do is I'm going to use these formulas that we had from 5.1. One of the formulas was the sum from 1 to n of I was n times n plus 1 over 2. Okay, so I'm going to use that here. The other formula that I had, well, one of the other formulas that I had was that the sum from I equals 1 to n of I squared is 2n cubed plus 3n squared plus n all over 6. I'm going to use that here for the sum of I squared. Okay. So I have 4 over n squared times n plus 1 over 2 plus 16 over n cubed, and then times 2n cubed plus 3n squared plus n all over 6. Okay, so let's take a moment to combine these up nicely. So n times n will give me n squared, and I'll also multiply in the 4. N times 1 is n, and then times the 4 will give me a 4n. And in the denominator here, I have a 2n squared. Okay, and my second fraction, I bring in the 16. 16 times 2 is 32. N cubed. 16 times 3 is 48. N squared. 16n 6n cubed. In order to evaluate this limit, what I'm going to do is I'm going to divide by the biggest power of n in the denominator for each of these fractions. So for this first one, I'm going to multiply by 1 over n squared on top and bottom. We have the limit as n goes to infinity of 4 plus 4 over n. And in the bottom, I'll just have a 2. My second fraction, the biggest power of n in the denominator is an n cubed. So I'm going to multiply by 1 over n cubed. So in the denominator, I'll just have a 6, and the numerator, 32n cubed over n cubed is 32. And I'll have plus 48 over n plus 16 over n squared. So as n goes off to infinity, these constants divided by n are going to go to 0. So I get 4 plus 0 over 2, plus 32 plus 0 plus 0 over 6. So I get 2 plus 16 thirds, or 22 thirds. Okay, this is a very tedious process, and we don't really want to make a habit of doing this. Just like if you recall from chapter 3, when we were looking at derivatives, we were able to compute a derivative using the limit definition, and then shortly thereafter we said, let's find some shortcut rules for that. We're going to do the same thing here. Okay, so we want to avoid this process. So one of the things that we're going to do is we're going to look at how we can make this connection between the integral and area, and we're going to evaluate integrals using geometry. And then later in 5.3, we're going to find a way to find integrals using antiderivatives. Okay, so first let's look at how can I evaluate integrals using geometry. So let's look at a couple examples. Find the integral from 2 to 4 of 2x plus 3 dx. And what we're going to do is, instead of looking at the limit of a sum, if I look at the graph of this thing, 2x plus 3 is a line. Okay, so we're going from 2 to 4, and so the integral that we're looking at here is going to be this area. And what I can do is, if you know the formula for area of a trapezoid, you can use that, or we can cut this up into a triangle and a rectangle and say that this integral is going to equal the area of the triangle plus the area of the rectangle. What I need to do is now compute out some values. If I plug 2 into this function, 2 times 2 is 4, plus 3 is 7. If I plug 4 into that function, I'll have 8 plus 3 is 11. So I can see that the triangle has a width of 2, a height of 4. So the area is 1/2 times 2 times 4. The rectangle has a width of 2 and a height of 7. The area is just 2 times 7. So we get 18 as the area of that region, which will be then the area of the integral. For this next example, I want to find an area that matches up with this integral, and I have to recognize that x squared plus y squared equals r squared is the equation of a circle centered at the origin. X minus h squared plus y minus k squared equals r squared is a circle that is centered at the point hk. Okay. If I were to take one of these and say solve for y squared is r squared minus x squared, so y is the square root of r squared minus x squared. Or solving this second one, y minus k squared is the square root of r squared minus x minus h squared. Okay, then I can recognize this square root as being part of this equation. Now, if you don't use the plus and minus, then instead of getting the top and bottom half, you will only get the top half if we just use that plus part. Okay, now if I look at my function, be squared anymore. There's no k here. It's just y equals this thing. So k is 0. And h is 3. So this is going to be centered at 3, 0. And my r squared is 9. So the r is 3. So what we have is a semicircle, radius 3 right here. And the area of a semicircle is half of the area of a circle, which is half of pi times 3 squared, which is 9 pi over 2. And what I want is the integral from 3 to 6. So I just want this piece. Okay, so that's just the right half. So I'm going to take this area of the semicircle and cut it in half again. So this red area is going to be half of 9 pi over 2, which is 9 pi over 4. So the integral from 3 to 6 of the square root of 9 minus x minus 3 squared dx is equal to 9 pi over 4. Okay, let's look at another example. Evaluate the integral from 0 to 2 of x minus 5 dx. I'm going to do this two different ways. First, I'm going to look at the limit definition of the integral. Okay, so we're going to say that this is the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x, okay, where the delta x is b minus a over n, which is 2 minus 0 over n, or 2 over n. The xi is a plus I delta x, which is 0 plus I times 2 over n, which is 2I over n. So f of xi is, since my function is x minus 5, it's 2I over n minus 5. Okay, so I'm going to plug my f of xi in for f of xi, and I'm going to plug the 2 over n in for the delta x. So we get the limit as n goes to infinity of the sum from I equals 1 to n, 2I over n minus 5, careful with your parentheses, times 2 over n. Okay, so I'm going to multiply things out. So 2 over n times 2I over n is going to be 4I over n squared. I get minus 10 over n. So now I'm going to break this up into two separate sums, and at the same time I'm going to factor out constants. So the 4 over n squared is constant relative to the sum. So I factor that 4 over n squared out, and I have the sum from 1 to n of I. And then over here, I just have the sum from 1 to n of negative 10 over n. Remember that if you have the sum of a constant, you get that constant times n. And for the sum from 1 to n of I, we have that n plus 1 over 2 formula that we just saw a minute ago. Okay. So continuing on with my limit, I'm going to multiply out this numerator, so we get 4n squared plus 4n all over 2n squared. Over here, negative 10 over n times n is just negative 10. If I divide by that n squared in top and bottom, then we'll get 4 plus 4 over n in the numerator and 2 in the denominator. Minus 10 hangs out. So I have 4 plus 0 over 2 minus 10, which is 2 minus 10, which is negative 8. And now we have a weird situation. My integral is negative, but areas can't be negative. So now let's look at a graph and see what's going on. So if I graph x minus 5 on the interval 0 to 2, the intercept is negative 5. When I plug in 2 for x, I'm going to get negative 3 for y. So the region that we're looking at is entirely below the x-axis. What happens here is we like to think of our integral as adding up areas of rectangles, but our formula doesn't actually have an area. It has two multiplied numbers, which we interpret as a width and a height. But here my function value is negative, so when I draw my rectangle, the function value is negative, so I'm going to have a negative value where I wanted to have height. Now, the formula doesn't know that I wanted to do area. It just says, okay, you have a negative value, you take that negative value, multiply it by that width, and you'll get a negative number, and you add up negative numbers and you'll get a negative. Okay, so integrals don't exactly give us area in all cases. What we want to do now is talk about, well, what exactly do they give us? Because we sort of started this journey talking about area, and they still do relate to area. So what we need to do is talk about something called net signed area. If this is a graph of my function y equals f of x, then the integral from 0 to 2 of f of x dx, when I add up the rectangles, right, I have this area 1 and I have this area 2 that's below the axis, and what I'm going to get from my integral is a1 minus a2. That stuff below the axis is going to count as negative. So it's not giving me an area anymore. And what we do is we call this value net signed area. We get something similar that happens if we have an integral that goes backwards. Let me show you what I mean. Let's suppose I have a function that's above the x-axis. And let's suppose my a is over here and my b is over here. So I have an integral from 5 to 1 of f of x dx. In my formula, when we look at the width of the rectangles, our formula is delta x is b minus a over n. But now that's going to be a 1 minus 5 over n, or negative 4 over n. So when I chop this thing up into pieces and I look at each of those pieces, what I want to be the width of the rectangle is a negative number. So it's not strictly speaking a width, because widths are not negative. But in my formula, I get a negative. So when I add all of this stuff up, it's going to give me a negative value. So the magnitude is the same as what the area would be. Right? So if this function, right, if this area was, say, 7, then this integral would be equal to negative 7. Okay, and if I integrated from 1 to 5 of f of x dx, then I would get the positive 7. Okay, if what I'm really interested in is just area, then the simple solution is just throw an absolute value on your function. Then it'll never go below the x-axis, and you'll be fine. Okay, so we could say, all right, if I want the total area, the actual area, we just put absolute values on, and then in my example above, it would just add those two regions. Okay, so let's look at an example of this. Let's suppose I want to find the total area between x minus 2 and the x-axis over the interval from 0 to 6. Okay, so what I can do to begin with, and maybe just to help this seem easier, is I can look at the graph. Okay, when x is 0, I'll be at negative 2. When x is 2, we'll be at 0. And when x is 6, we'll be up here at 4. So when I want the total area, I want this area 1, and I want this area 2, and I want those two added up. Okay, so then what we could do is we could say, well, the total area is the integral from 0 to 2 of the absolute value of x minus 2, and then the integral from 2 to 6, and here it's above the axis, so I don't have to break it up. I could just take the x minus 2. Okay. Now rather than use a limit of a sum, now I can just use geometry. If I want to find the total area, I can say, okay, for this first piece, I have a triangle. The formula for area of a triangle is 1/2 base times height. The base here is 2. The height is 2. For the second one, I have a triangle, 1/2 base times height. We're going from 2 to 6, so the base is 4, and we're going from 0 to 4, so the height is 4. So I have 2 plus 8, or 10. So this is the total area. However, if I were to find the integral from 0 to 6 of just x minus 2 dx, a1 would count as negative. Right? So that first area we found was 2, so it would be negative 2, and the stuff above the axis would count positive. So I would get 6. Notice that like 6 has nothing to do with 10, right? I can't really cover the 10 from just looking at the 6, so we have to be very careful with what it is that we're trying to find and how we interpret area. Okay, so this leads us into some properties of integrals that, goes beyond just area a little bit. Here's our first property. If I'm looking at a region and I start and end at the exact same spot, then I don't really have a two-dimensional region anymore, right? If I think about a graph here, and here's my function, and there's just a, and that's it. It's just a. There's no, I'm not going out to anything. I can't form a rectangle with any width, so I just have, 0 area, right? So if we start and stop at the same place, it doesn't matter what the function is, we always get 0. Okay. The next property, if I take an integral from a to b of a function, that's the opposite of the integral from b to a of that function. If you flip the limits of integration, you get a negative out front. And that goes back to what we were talking about up here, where if my b is 1 and my a is 5, if I have sort of this backwards looking integral, I end up with a negative number because the widths all come out as negative. Okay, the next one, we sort of already used this, but it does indeed work. The integral of two added functions I can break up as separate integrals. Okay, we did that in our last example. Also, constant multiples factor out. Okay, that seems to make sense. They factor out of limits and sums. They should factor out of integrals. And then this next one, we have to be a little bit careful with, and I want to explain this last property. The integral from a to b of f of x dx. So let me start by drawing this. So let's suppose I have a function f of x, and we take the integral from a to b. So I'm looking at this area that is equal to the integral from a to c. So let's suppose I put some c in between. I could instead take the integral from a to c and then the integral from c to b. And that makes sense. It's just like you're taking your region and splitting it into two pieces and then adding those two pieces up. That makes perfect sense. Except that there's no condition that c has to be in between a and b. This property works, and I'll redraw it. Okay, let's suppose I have my a and my b just like before. And let's suppose that the c is somewhere off to the right. Then on the left-hand side, I have the integral from a to b, which is this region here. Okay. And then the claim is that that's equal to the integral from a to c of the function. So all of this plus the integral from c to b. Now what I want you to notice about the integral from c to b is that because c is to the right of b, I'm integrating backwards. So this part counts as negative. So when I take that integral from a to c, and then the integral from c to b, that c to b part counts as negative, and it'll wipe out all of that overlap. And so I will just get that integral a to b portion. So what's really nice about this property, because of this net signed area thing, I don't need c to actually be in between a and b. This property works no matter what. And that's going to turn out to be really useful because there will be some times where we either don't know the limits of integration, or we'll even see in the next section we could have a limit of integration that's a variable. But we'll hold off on that for now. Okay, so let's look at some examples. Let's suppose I don't know the function, but I do know some values of the integral. So let's say that we know the integral from 0 to 8 of f of x dx is 10, and the integral from 0 to 5 of f of x dx is 5. Find the integral from 5 to 8. Okay, so what I can do is I can say the integral from 0 to 8 of f of x dx is equal to the integral from 0 to 5 of f of x dx plus the integral from 5 to 8 of f of x dx. That's that property 5 that we just looked at, right? If I go a whole region, I can split it somewhere in between. Okay, so then what I'm going to do is I'm going to replace my pieces. This integral 0 to 8 is just equal to 10. This integral from 0 to 5 is equal to 5. So if I want to know the value of the integral from 5 to 8 of f of x dx, I could just subtract 5. If we wanted to be really fancy, we could get this done in fewer steps. What I could do is I could say that the integral from 5 to 8 of f of x dx is equal to, remember that when I use this property, I throw a c in the middle, but the c doesn't have to be in the middle. So I can think of my c value as being 0. So I could say, okay, that's the integral from 5 to 0 plus the integral from 0 to 8. And I know the integral from 0 to 8. I don't know the integral from 5 to 0. I want to flip that over. So if I flip that over and make that an integral 0 to 5, that just puts a negative on it. Okay, so now I have negative. This integral from 0 to 5 I know is 5. The integral from 0 to 8 of f of x dx is 10, so negative 5 plus 10 is 5. So we get to the same spot. It's just sort of another way of setting this up and using my properties of integrals. Okay, let's talk about average value of a function. Now, before I get into exactly what the average value of a function is, let's do a quick review of what an average is, right? So if I take some numbers, right, if I look at this set of numbers, right, 2, 5, and let's say 11, just look at those three numbers. Then the average is 2 plus 5 plus 11 divided by 3. Okay, so I add them up and I divide by how many numbers I have. Okay, and I get something that represents sort of a middle point. Okay, so a way to think about the average is if I were to take a number line, and let's suppose that at these different spaces, think of my number line as being like a physical bar, and let's suppose I put a weight at each of these spots at 2, 5, and 11, then this bar would balance at 6, right? So that would be like the balancing point, right, where I have just as much stuff on the left as I do on the right. Okay, and you can see, well, I have more points on the left, but they're closer in. Okay, and so it would balance, right? You can think of like a teeter-totter, right? If you're further out, it puts more torque down and it can offset a greater weight. Okay, so that's regular average. When we look at a function, though, a function, if I look at it, say, an interval from a to b, I have infinitely many values. So when we're talking about average value of a function, what we want to do is think about, well, how do I average an infinite number of values? You know, I would have to divide by infinity, and that doesn't really work. Okay, but instead I can think about this idea of things balancing, having just as much stuff on both sides. Okay, so to give you maybe an intuitive idea, let's suppose I have some function, here's y equals f of x from a to b, okay? And if I think about this thing, think about this as being like maybe a block of ice in a container or something like that. As it melts, the stuff from the top will flow down to the bottom, and I'll have like a nice level amount, where this stuff up here can fill in this gap down here. Okay, then that would be that average value, where I have the same idea of sort of the, I don't know, leveling things off or you know, evening things out, right? Instead of numbers being all crazy different distances, we have sort of a nice middle balance point. That's how I would create a middle balance point with average value. I want to say, all right, all the stuff above will fill in the missing stuff below. All right, so let's look at what that looks like as a formula. Let f of x be continuous over an interval a, b. Then here's how we get average value of a function. What we do is we take, instead of adding up the numbers, we look at the integral, which is kind of like adding up all of the function values, right? That's what we did with the, you know, if I think about my limit definition, if I think about 1 over b minus a times, and I write my limit definition, I have the height of the rectangles times the width of the rectangles. And of course, these are infinitely many rectangles, okay? And b minus a, if I add up all of the widths, that's b minus a. So if you think about the b minus a as canceling the delta x's in some sense, then what I'm doing is I'm just adding up all of the heights. Okay, and so that's where you get this idea of averaging. Okay, but this is just a definition, right? So you can always just follow this. You don't have to necessarily understand it, but maybe that helps. Okay, so let's look at computing this. Find the average value of f of x equals 6 minus 2x over the interval 0 to 3. I need to, well, let's write out average value is 1 over b minus a, integral from a to b of f of x dx. The b is 3 and the a is 0. This is 1 over 3 minus 0, integral from 0 to 3, 6 minus 2x dx. And I need to evaluate this integral. And what I'm going to do is I'm just going to interpret it as an area. So when x is 0, I'll have 6. When x is 3, I'll have 0. So I get this line here. So the area under the graph is this nice neat triangle. And so the area of that triangle is 1/2 base, which is 3, times height, which is 6. And 1/2 times 3 times 6 will give me a 9. So the integral from 0 to 3 of 6 minus 2x dx is 9. And so I have 1/3 times 9, which gives me a 3. Okay, so that's saying that the average value of this function is 3 over this interval. Okay, that's it for section 5.2.